Alrighty, well, we're going to go ahead and get started. This camera is way out of focus. That's a little better. Okay, turn on the projector so everyone can see what I'm doing. But we're talking about cool things today.
Sure. Interesting.
I've been told that lie before.
I even have color slides today.
Color on the slides?
I have color on the slides. Can you believe that?
Oh, man.
I'll believe it when I see it.
Come on, projector. Are you working yet? Okay. So this is what we're going to talk about today.
C++.
Templates. All right. So my goal today is to not make you all experts in templates. My goal today is to at least introduce them enough so that you can feel comfortable using someone else's expert templates. Okay. Such as Eigen or, whoever else. And to understand a little bit of what's going on.
So Eigen is considered a template?
It's considered a templated library.
Okay.
Templated header library, I think, is the real
Alright, now you're just
term.
confusing me.
It means it has no .c files. It's entirely .h files. There's nothing for you to compile in order to use it. All you have to do is include the correct .h files.
Okay.
Because the compiler does all the compiling.
Oh, so we don't have to pick through and say.
Anyway, so templates are a form of generic programming. This is not unique to C++. Other programming languages have this same kind of thing. But the idea of a template is it provides a blueprint or a pattern for what a function or a class should look like. They allow the use of code reuse. It's a little redundant, but yeah, you write the function once and it works in multiple situations. So it reduces bugs, reduces code maintenance. Also, templates are a form of functional programming. And this statement may or may not be true. I read something yesterday that may or may not be true, but it's basically a programming language inside of another programming language. And when you get into the really advanced uses, you call it meta-template programming, because you're telling the compiler to do the programming for you, which is kind of interesting. So this is the first situation that templates were designed to solve. This problem here is we have, and here's my color. Hey, don't do that. Okay, so let's say you want to implement a max function in C. Okay, first off, you can't overload functions. So you have to have an I max, an F max, a D max. Okay, and they all do the exact same thing. You'll notice that this line here is exactly the same in all of them, but we've had to type it, or at least copy and paste it several times. And this one's for integers, floats, and doubles. Okay, so templates were first introduced to solve this problem. But before we get to that, C++ at least allows us to overload the max function. So now we don't have to have an I max, an F max, a D max. We can just have max. And the compiler figures out which one we're talking about depending on what types we give it. Okay, so we can at least do that much. We've simplified the problem a little bit.
So should that
Go ahead.
Should that be a double on the double?
Yeah, that's a copy-paste error. Sorry. And that's why we don't like copy-paste errors. Alrighty, so, however, C++ templates allow us to write one function. And we do it we have the template keyword, and then we use our little angle brackets here. And we say we're going to have a template, and we're going to have a type name T. It's a placeholder for the actual type. Okay. And so wherever we would use the type, we're going to use the big capital letter T now. And we can name that whatever we want. We could call it type name my type or type name elephant. And then we'd use elephant wherever we wanted the actual type. Okay. But capital T is pretty standard from what I've seen. Anyway, so we define this one function here. And then we can use it multiple times. If we have two doubles, we can do max of A and B. If we have two integers, we can do the max of A and B. If we have two of my class, can we do that?
If your class is overloaded with the comparison operator.
Exactly. If your class has overloaded the comparison operator. So this third instance will not work if you haven't defined what A less than B is for your class. The compiler knows how to do that for doubles and integers, but it doesn't know how to do that for your class. So you have to specify what that is. And there's a few different ways to do it. So if this is our generic function here, this is what's called the base function template. Okay, it's important to realize that this is not an actual function. This is a template, a pattern for what your function should look like. And when you go to use that function, the compiler then builds the actual function. Okay, they're two different things. So we can actually provide what's known as a specialization, okay, using this right here. We tell it this is a template where we've defined now the types, okay, and we're returning my class. We have max, and this is a max my class function, all right, and you'll see we don't actually do any max or minning here. We're just returning one of them, which is bad, just so you know. So you can do this, or the other option, you can actually just write a normal function. And this overload, this is an overload for the base template. And so those are two options there. And it's important to note that the non-template function has greater precedence over the template specialization or the base one. Okay, so the non-templated function is more important, and the compiler will choose that first if you provide it. So anyway, it's generally not, you generally don't want to overload, do a specialization of the template. You'd rather do an overload of the function. Okay. However, the best option, even bestest, we should write that here, as Ted mentioned, is you overload the less than operator in your class, at which point the original template will work just fine. Okay. And the standard library uses this pattern all the time. If you want your class to work in the standard library in certain situations, they tell you what you need to do is overload the operator for your class.
Can you explain what that means? I don't really know about that. Overloading operators.
Okay, we can go over that a little bit.
Probably a juvenile question.
No, it's fine. Yeah, go ahead and keep those.
I was never formally taught C++, so I feel like I haven't.
Well, I wasn't either, so
Dang it.
I've just been at this a really long time. Can I blow this up any? Can you see this, or is it too small?
I can see it.
You can see it? Okay. I don't know, maybe there's a preferences or something.
Probably in settings.
Settings, preferences, font size, editing. Anybody see fonts? I don't see it.
It might be in general. Is it not in general? No.
Seriously? You'd have a font or something.
Enable smooth font.
Okay, well, whatever. You can see it, so
Close enough.
strain your eyes and go get LASIK tomorrow. So, all right. So if we have a class, whoops, I don't want caps lock. And we have something in here, and of course we need our constructor, which takes another one like this, and do a underscore a like that. Okay.
I don't understand what that syntax is.
Down if you hit control and scroll up. We'll zoom in.
Ooh, there we go. Okay. This is just a constructor.
Oh,
That's all it is. And we have a destructor. I forgot this thing here. Okay, so now we can actually overload the less than operator. And how this works is something like, let's see here. Yep, I think it works like this. Um,
neither right now. There's no way.
Okay. So, I think we also, I don't know. It's similar to this. So, basically, what it's saying is, whenever if we wanted to use this kind of syntax, so if we had and then we'll have another one, call it C here. Oh, this is supposed to be a Boolean, isn't it? That's what it is. I remember how this works.
What's some of these words?
Something like this. We can actually use true. Yeah, we'll do this. True and false. And this may or may not be perfectly correct, but we can then use this in statements such as this. So we have two objects of my class, one storing a 1 and one storing a 2. Okay, and we want to say if A is less than B. Now we can do that if we were just using 1s and 2s or doubles or ints. But the compiler doesn't understand this because this is not a double or an int, this is a class. Okay. So basically what we're doing is we're telling the compiler, we're giving it a function of how to use this particular operator.
Okay, so how do you... I understand what you're trying to do. I don't understand how it works, though.
So how it works...
So, like, how can you compare if one class is bigger than the other?
Well, that's why you have to tell the compiler what that is. You define how to compare two objects of the same class.
Okay. Oh, two objects
Of the same class. Yeah, so here we have two objects, A and B,
Okay. Okay.
right?
Okay.
Does that make sense?
So the way you defined it up there, it's just having to do with A.
Exactly. So we have this variable A here. Okay. And so what I'm saying is that in order to compare two objects of this class, the variable A has to be less than the other variable A in the other object.
Okay.
Okay?
So when you say overloading an operator, you just mean making it work while using classes or structs. Well, classes.
Correct.
Okay.
Struct and class are pretty much the same thing in C++. So
It's kind of like what you do with a copy constructor, or like sometimes you have to overload the assignment operator. Like when you have to do like a deep copy. That makes sense.
yeah, so anyway, that's the basic idea, is we're telling the compiler how to compare these two objects
Okay. And so
using this function.
So if you were to use that to compare classes, it wouldn't throw an error. It would know what to do with it.
Exactly.
Fair enough.
Yeah.
By the way, my excuse is that I'm not as smart as you, so that's why I didn't.
That's a lie.
No, it's not.
Anyway, so the best option is to overload the less than operator, at which point then the compiler understands how to do this max function, how to build that max function. All right, so getting a little more advanced, templates can work in a recursive manner, and that's generally how you see them being used. So you can have a function that calls itself. So if we have a factorial function, and we're actually going to template this on the integer n. So instead of doing a type, now you can actually do an integral value. And so you can use integral values, you can use enumerations, or you can use anything that the compiler can turn into an integer at compile time. There are a few other situations you can actually use functions and variables, and you can actually like pass a variable name into a template. It's weird. Anything the compiler knows at compile time you can use as a template, but those are a lot more advanced, and I don't know why you'd use them, honestly. Anyway, so the idea here is you can actually get the compiler to set this up, or to compute the factorial at compile time. So this template here, it's telling it to return n, and we all know the definition of a factorial, right? N times n minus 1 times n minus 2, and so on. Correct? Okay.
Yes.
Anyway, so you tell it we're going to template this function on n, and we want to return n times the factorial of n minus 1. And the factorial of n minus 1, this is an entirely different function. Because you remember, this is just a pattern. And so the compiler builds a n factorial, which tells it now needs to build an n minus 1 factorial. And that one tells the compiler, oh, you need to build an n minus 2 factorial. Okay, but we have to tell it where to stop. And so we actually have to specialize a certain case. And so I chose to specialize the factorial 0 case, which just returns 1 and stops that recursive train. Otherwise, we'd get down into the negative numbers and on to infinity until your compiler ran out of memory. And that would be bad. And so you can actually say integer a here equals the factorial of 3. And I should probably, oh, well, whatever. Anyway, and so what happens is the compiler now says, okay, factorial of 3 function, that equals 3 times factorial of 2 function. Well, that equals 3 times 2 times the factorial of 1. And that equals 3 times 2 times 1 times the factorial of 0 function, which we've defined here. And in the end, we get 3 times 2 times 1 times 1. Well, now the compiler has all the information it needs, and it can compute 3 times 2 times 1 times 1 up front. At which point, it can, instead of doing all these functions at runtime, this basically turns into integer of a equals 6. That's what the compiler does if you have function inlining going and stuff like that. And so this is also the reason why C++ takes so long to compile stuff. Is the entire standard library is templates, and so it's sitting there processing templates the whole time. Templates can also be assigned default values. So we can say the default value for that is 2, in which case you can now call it without the square brackets, or you can call it with the square brackets, in which case these two things are the same. Okay. All right. So that's basic function templates. Then we also have the class templates, and this is where they are a lot more useful, actually. Because you can template your class to use type T. And so now, whereas before we had my class, which had a double, we can have a my class that holds an integer, could hold a character, could hold a string, could hold a vector, could hold any number of things. The standard library is full of classes which are templated. We have the vector class. Okay. So we have a vector of doubles or a vector of ints. And what's important to realize is that those two classes are two completely different classes. All you did was provide a blueprint for what the class should look like. And when you actually use it, then the compiler goes and actually builds that class. And so we have two completely different types. We have a vector of doubles and a vector of ints. Those are not the same, and they're not equal to each other. You can do a standard array here, and this is actually, we have two templates. We have the type of the array and then the length of the array, which the compiler has to know at compile time. You can nest these things together, so you can have a standard vector of my class, which is of type double as well, because we have our templated class up here. So nested templates, it gets really hairy. Now, here we have another object, my class int. I'm going to call that variable e. And we want to push e back into d. However, this doesn't work because this is my class double and this is my class int. These are two completely different types, and you can't convert between the two. You can also specialize class templates for certain situations. So here we have a class which is templated on two different parameters. Okay, we have the type and an integer n. And you see it holds a t array of size n. Just for simplicity's sake, we can do a partial specialization. So we have the template, and now you notice we've eliminated type name t because our partial specialization is on a double. Okay, but we still allow n to be any size that can be specified. Or we can do a full specialization in which we just use these empty brackets here. And then you'll notice that I've actually kind of broken the rules here, or the pattern. This full specialization of type double and size 10 is actually an integer with a variable named b, and it's of size 20. Okay, and you can do that. This is legal. If you were to type my class double 10, then you would get a class that holds an integer of size 20, an integer array of size 20. And so You can break the pattern, but it's generally a bad idea because then the programmer has no clue what's going on. The compiler does not compare the previous template with your specialization. It's just going to use it. Last thing is variadic templates, and these were added in C++ 11. And so they allow for any number of template types. And so we have this first one, it's sometimes called the head, and then we have the everything else. Okay, and so this is a function, a variadic function, as they call it, and he can take any number of arguments. Okay, so we have type name t, this variable t is a head, okay, and then he also has everything else, okay, and he returns the head plus then the sum of everything else. Again, that dot 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 there means everything else. So, and then we have to specialize for a specific case. And so in this case, we specialize for what happens when we only have one parameter left. So if we look down here, we have an implementation of this. So we have the sum of 1 plus 2 plus 2.4 plus 6. I can get this thing up here. And so what this turns out to look like is we have the sum of 1.0 and everything else. Okay, this returns 1.0 plus the sum of everything else. And this is now the sum, or I should say this returns 2.0 plus the sum of everything else. And that returns 2.4 plus the sum, and I've run out of room apparently, of everything else. Why is this pen not working?
Maybe it's out of ink.
Maybe it's out of ink. Maybe it is. Anyway, this last one here is plus then the sum of just the last one is 6.0, and this uses the specialization over here, which just returns 6.0. And so you work your way back up the chain. This is 6. So we get 2.4 plus 6 plus 2 plus 1. And then the final answer gets returned. Go back. Okay. And so this variadic template here now accepts any number of arguments, which is kind of cool. And with the function inlining, basically what this turns into then is just 1.0 plus 2.0 plus 2.4 plus 6. And the compiler, in this particular case, can actually calculate that at compile time. So you can also use variadic templates for classes. And so we're going to define our first type and then everything else. We're going to call it the tail in this case. And so this is really cool. We can build a cascade of classes. And so we have, this class has 2 variables. All right. And I think there's supposed to be a dot, dot, dot there. But anyway, the first variable being t, a variable of type t. Okay. And the second variable is a my class, which contains the tail. All right. And so basically what we get is we get A, and then inside this other class, we're going to get another A, and inside the other class, we're going to get another A, and another one. And it cascades down until it comes to our specialization here. And our specialization is in if we have 1, in which case we stop. We don't have this last my class tail anymore because we have no more tail. And so that stops our recursive progression. And so you can actually build a struct at compile time without ever having to actually write the struct in this manner. This is the basis for the standard tuple class. It's a funny word, tuple. Tuples are nice because they let us return multiple values from a function without having to define a new struct. And so here is an example of standard tuple. We have an int and a character and a float and then a vector of doubles and then a string. All those things are packaged up together into this one object B. Okay, so that's kind of cool. That's a variadic template for you. So anyway, last slide, I believe. Magic of templates. This is obviously just the basics to get you familiar with the concept and how it's used. You can do a lot more advanced and complicated things. The Eigen library uses templates to do linear algebra almost as fast as LePac, in some cases faster than LePac, which is kind of the standard of golden excellence. And they do it in a very nice and easy to use fashion. Whereas LePac, you have all these complicated interfaces and it's really nasty and hard to link to. Whereas Eigen, you just include eigen.h and you can do stuff. You can do matrix multiplications instead of having to call this nasty matmul function. Really? Really? Whoa. I don't know what just happened. So in LePac, you have to do, if you want to do a matrix inverse, you have to call this like gem, and it has like 12 parameters if you want to do a matrix inverse. In Eigen, you do E dot inverse. And what's amazing is behind that you have hundreds of templates behind that are crazy. I learned from Eigen how to do a lot of these things. Also just reading my own stuff, and so I wrote my Fort C++ class. Uses templates to eliminate temporary objects and form complete loops over arrays. So basically what that means is the templates allow this statement here with these two arrays to turn into that. The compiler turns this statement into that loop for me, and I don't have to do it. The Catch unit testing framework, which I've used, uses templates plus macros to create a nice, clean, simple framework. And this is really cool here. I found this a few weeks ago. This guy uses some templates to create a very Pythonic syntax for iterative loops. Basically what he does is you take this here, which is the C++11 range-based for loop, and he adds this function called range from 0 to n, and it turns into that loop there using his magic templates. And they end up being identical. The compiler takes that and goes through all the template magic and simplifies it all down into that loop there. So anyway, if you really want to get into templates, I mean, that's probably why people like it so much, is they feel smart because it's really, really complicated, and they feel smart that they invented something complicated. But anyway, so that's the basics of that. I was also working on this here, so maybe we'll go through the first part of this since we still have time. The C++ exceptions. So exceptions deal with error handling. Every real world code needs some way to handle errors or situations that the code was not designed to handle. And so there's a few different ways we can handle errors. In C land, there's a lot of error codes. Every function returns an error code. In fact, every single MPI function technically returns an error code, but we've been ignoring that fact this whole time. We just generally let the thing kill itself if something bad happens. So The first option is you return an error code. Oh, bother. First option, you return an error code, okay? Second option, you have an argument called the error argument, and this is actually supposed to be a reference, now that I think about it. And so this square root with error function is kind of a dumb function, but hopefully you get the point. It sets the error variable, and that's something that you can then look at after the function is returned. You could define your function to do something specific in case of an error. So in this case, if a is less than 0, instead of returning the square root, it just returns a. Or you could just ignore the fact altogether. Okay. So there's some ways we could handle errors, but here's some problems. What happens if the programmer accidentally or intentionally, as we've done with MPI, forgets to check the error code? Also, you have to have correct documentation, and someone has to read it and understand it. Memory management, this is kind of the big one. If an error occurs after memory has been allocated inside of your function, then you should clean it up before returning. And then if there's multiple places where an error can occur, you have all this cleanup code throughout the entire thing. So I'm going to show you an example of confusing and useless error handling.
An error has occurred.
Anybody seen the blue screen of death? Here's the error code. 0E016FBFF9B3D4. Is that helpful? Does that tell you what happened? Not really.
You understand?
If you have, maybe if you have the Windows reference manual in front of you, you can look it up. And they've gotten better at this, by the way. We could make it slightly better by.
When I was trying to switch my wife's laptop over to Windows 10, I kept getting those kind of errors and Googling it, nothing.
Nothing.
They don't just give you a weird code now, though. It's more like a string of letters that are like a shortened version of what the error is.
Yeah, so we could make this slightly better by using enumerations. So we have this error enumeration, in which case we could have our square root function now returning error square root negative or error none. And that's something you could check and it'd be a little more readable. But again, if you don't check it, then you never know. Or you could have special error handling libraries. I've seen that before. Anyway, C++ decided to take a different route, and they do it using exceptions. So an exception is something that can be thrown and caught by specific error handling code. They're used in many different languages, especially the newer ones. They can be implemented in many different ways. How they're implemented changes how they are to be used. So what I mean by that is in C++ land, exceptions tend to slow your program down a lot. There's a lot of stuff that goes on because of the way they're implemented. However, in Python, they're implemented differently. And so they actually encourage you to throw exceptions. They're like, does something not work? Well, they should actually, it's like, they just say open the file. Don't check to see if the file exists. Just open it. And if it doesn't exist, it'll throw an exception. And then you can say, okay, well, now it doesn't exist. And then you can move on from there. Whereas in C++, they say, well, you should probably check first, because throwing exceptions is generally a bad idea. Because it slows your code down a lot. But here's an example. So here's our square root function again. And we're going to say if x is less than 0, I'm going to throw an integer 0. Okay. So here's our actual function. We set x equal to -1 so that this exception will get thrown. And what you do is you write a try block. Okay, and inside the try block, you put your code. At the end of the try block, you put a catch block, and you tell it what you want to catch. So in this case, we want to catch an integer. And we're going to store that into the variable e. And then inside the catch block, we put our error handling code. And so we say, if e is equal to 0, then we want to output negative number. Okay? And so the catch block only gets run if an exception is thrown. And so that's one way you can actually physically separate out your error handling code from your actual program code. So in this case, the x equals -1, we go in here, we say x is equal to square root of x, so we're just overwriting our x. So in this case, I want to ask the question, what is this value here? And if it's still -1, because
Where is that E coming from, or where?
let me
Oh, so you're.
let me clean this up a bit.
Oh,
You declare it.
Okay, so
So
let's catch it. Okay.
we throw the 0, and what happens is it looks for any try catch block in the immediate function. But we don't have a try catch block. We don't have try in here anywhere. Okay? Since we don't have it, what it does is it immediately exits the program, or not program, but function,
Throws it to someone else.
and it throws it back up the stack to the function that called this one. Does that make sense? So it throws it up the stack, and then it throws it to here. So now it comes into here, to this line. It says, hey, I'm in a try block. Okay. And then it jumps to the appropriate catch block. You can actually have multiple catch blocks that catch different things, like so.
So the 0 that got thrown, it goes up a level and it's caught by the catch statement.
Yes.
What would have happened if we didn't have the try?
If we didn't have the try, okay, if we didn't have any of this,
Yeah.
that was a horrible noise. Basically, we get to this part. The program exits, and you get an abort, and you'll get a big error message and lots of garbage that gets printed out. Okay. Yeah, that's the wrong one. And so, anyway, yeah. Another important point is that it immediately exits the function, and then before it does that, it actually calls destructors of all the objects in the function. So that way it cleans up your memory, which we noted before was one of the problems. Anyway, propagating up the stack is also known as unwinding the stack because it destroys stuff as it goes along. And so that cleans up the memory. It causes some issues. I know that the guy that invented Linux thinks that this is the stupidest thing on the planet, which is why he still writes in C and not C++, even though several people have tried to tell him to move to C++. And he's like, this is one of his big things. I hate this idea. But anyway, that's as far as I got in making the slides, and it's time to go anyway. So I will continue this tomorrow a little bit. But that's the basics of exceptions. Anyway, so you probably couldn't see me that whole time. Anyway, good luck on everything. We got quiz due Saturday, project due Saturday. I've already explained the extra credit project, so please email me with any questions that you have. We'll talk to you guys later.